Hello and welcome to another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 3, Lesson number 6 on piecewise linear functions. So piecewise functions, well, you saw those in Common Core Algebra 1 quite a bit. We're going to see them a little bit on and off this year, and you see them a lot in pre-calculus. And the idea of piecewise functions, whether they're linear or otherwise, is very easy. We simply use different formulas over different parts of the function's domain to form, let's say, a more complicated rule that converts inputs to outputs. Yet, a function is a function, right? So for any value of x in its domain, there can be only one value of y. Keep that in mind. All right, let's jump into some piecewise linear problems. So, exercise 1. Consider the piecewise linear function given by this formula. And I'm not going to read the formula off, but let's start talking about how to think about it. It says create a table of values below and graph the function. All right, well, let's do this by hand. So when we have an input of -3, what the piecewise function has to tell us is which one of these formulas to use. Well, it says that we should use the formula x minus 3 for every x value that's greater than or equal to -3 and every x value less than 0. So if I put -3 into that function, well, -3 minus 3 is -6. If I put -2 in there, -2 minus 3 is -5. If I put -1 in there, -1 minus 3 is -4. So I'm thinking I'm seeing a pattern here. Now, if I put 0 in there, and I know that the formula doesn't apply at 0, notice 0's not there, I'm gonna put a -3 here. I'm gonna put a little dashed line for a second. Now, I realize that's not actually its value, but I'm gonna have it there anyway. This is now when I'm going to transition over to the other formula. So when I put 0 into this formula, 1/2 times 0 plus 4, well, that's going to be 4. When I put 1 in there, right, it's a little bit more annoying, but I get 4.5. Okay, fair enough. When I put 2 in there, right, I'll get 5. If I put 3 in there, I'll get 5.5. I think I see the pattern. It's just going up by 1/2 every time, and I'll get 6. So let's plot this thing. At -3, 1, 2, 3, we have 1, 2, 3, 4, 5, 6. At -2, 1, 2, 3, 4, 5. -1, 1, 2, 3, 4. Now at 0, I'm going to have a 3, but I'm going to draw it as an open circle because that point's not really on there. So this is that part of the formula. Now really at 0, what I really have is a +4. And then at 1, I have a 4.5. 2, I have 5. 3, I have 5.5. And 4, I have 6. So I have that. All right. Now, letter B says, state the range of f using interval notation. The range. Now, the range is all the y values. It would be tempting to just say, it would be tempting to do something like this, -6 to 6, right? Because that's the smallest y value, largest y value. The problem is there's this whole stretch of y values in here that we don't hit. So they're not part of the range. We can't do that. In fact, the range starts at -6. It goes all the way up to -3, but it never hits it. That's why I needed to calculate that thing. Union, this is what's called the union symbol. It joins two sets together into their union. Well, then we pick it up at 4, and we go all the way up to 6. Notice square brackets on both of those things because we do hit 4. So that's a much trickier range than what we're used to. We're used to just saying, here's the smallest y value, here's the largest y value, and you go everywhere in between them. But this is what's known as a discontinuous function. Remember when we talked about continuous functions a little while ago? Well, this is a discontinuous function. There's a break in it, a gap. And that often happens at what I would call the cutoff point on a piecewise function, where we transition from one formula to the next one. All right, pause the video now if you need to. I'm going to clear this out. Okay, let's keep working. Now, in the last problem, we took a piecewise linear function whose formula was given, and we changed it into a graph. Here we're going to go in the exact opposite direction. We're going to take a graph and we're going to change it into the formula of a piecewise function. This is pretty challenging. Okay, now let's just take a look at the graph. Let's get a lay of the land. Okay, there's really three distinct portions. So ultimately, whenever I write a piecewise formula, f of x equals, we use these funny brackets. Now, we're going to have three formulas, 1, 2, 3, and 3 intervals. Okay, that's what we're going to have. So let's tackle this first one. All right, that's a linear function. So section 1, if you will, y equals mx plus b. So I really have to figure out m and I have to figure out b. This one's going to be kind of a little weird, but let's play around with it. Can we figure out what m is just from the graph? Let's grab this point and let's grab this point. What do? We have to go over 2 and we have to go up 3. So that means m is 3/2. Now the weird thing is it doesn't strike the y-axis, but if the line was extended forever, it would. And it would hit the y-axis at 1, 2, 3, 4, 5, 6, 7. So that's b. So that first formula is 3/2 x plus 7. Now, what's its interval? Well, 1, 2, 3, 4, 5, 6, 7, 8. Well, it goes from -8 is less than or equal to x is less than or equal to -2. You might wonder, well, that didn't work out very well. Let's -8 less than or equal to x less than or equal to -2. Now, it'd be fair to kind of ask right now, why did I put the equality there? Why didn't I leave it off? Well, notice this is a filled-in circle, right? It's not an open circle there. It's filled in, that dot. So certainly that formula does apply when x is -2. You can even check it. Anyhow, I'm gonna get rid of, now I turn my eraser to being small, I'm gonna get rid of all that writing. And I'm gonna go back to my pen. Let's go with the second section, this one. Now that's actually pretty easy. And the reason that's easy is that is a constant. Okay, that is an absolute constant. So it's a little different. It's just y equals a number. And the question is, what's that number? That number is just 4. So as weird as it may look, as weird as this may look, the second part of this formula is just f of x equals 4. Now what's my interval? Well, interestingly enough, I could put the less than or equal to signs there, because that formula does apply there. It almost seems like this wouldn't be a function, but I'm going to leave it off just so there's no confusion. And I'm going to say x is less than or equal to, let me call it 3, right? That's -2, and that's 3. And again, you could have the equal sign there and not there. Same deal there. All right, let's go for that last little section, okay? So I'm going to get rid of this. Get rid of these two, hopefully. Now I'm looking for that. 1, 2, 3. Okay, well, let's try to figure out, again, it's a slanted line, so it's y equals mx plus b, m. Well, one thing that's important to note right away is that m is negative, right? Because this thing is decreasing. Now it goes down 2 for every 1 that it moves to the right, so the slope's -2. Now, what's its y-intercept? Well, let's see. If I do this, oh, I run out of graph paper. Now, a pretty sophisticated person, even if they run out of graph paper, can still figure out what it's going to be, right? But let's say for some reason it was harder than that. Notice how the point 3, 4 lies on this graph, right? This point 3, 4. We could actually use that with the point slope form. In fact, we could even put the point slope form in for that. But I'm going to rearrange this into y equals mx plus b form, given that that's what all my other lines are in. So there is the correct formula. Negative 2x plus 10 for 3 less than x less than or equal to 1, 2, 3, 4, 5, 6. And there's our final answer. This is a big problem, getting through all of that. But very doable. We just have to find the equation of 3 lines, one of which is very easy, y equals 4. Okay, well, pause the video now. Think about this. This is kind of a challenging one. All right. Now, piecewise functions can be very challenging, especially algebraically. All right, because they have these different formulas for different parts of their intervals. So let's play around with another piecewise function. All right, here we have g of x equals, that function. Letter A says determine the y-intercept of this function algebraically. Algebraically, then it goes on to say why can a function have only one y-intercept? So anyway, think about this for a little bit. Pause the video and consider both questions. Well, to find a function's y-intercept algebraically, we always do the same thing. We plug x equals 0 in. The question is, which one of these two functions does x equals 0 lie in? Well, it's got to be the one for this interval, x less than 2, because 0 is less than 2. So 5 minus 0 gives me 5. That's my y-intercept. Okay, and it can have only one because there can be only one output for x equals 0. Now letter B, find the x-intercepts of each individual linear equation. X-intercepts, not y-intercepts, x-intercepts. Well, let's do it. Like for the first equation, to find x-intercepts, remember we always set the function equal to 0. This is pretty easy. I'm not going to do much to solve this. I'm going to get x equals 5. The other one, a little bit more work, 1/2 x plus 2 is equal to 0. That would give me 1/2 x is equal to negative 2, and x must be negative 4. So those are the x-intercepts of those individual formulas. Letter C, graph the piecewise linear function below. All right, well, one thing I'm going to do, I'm going to put a little, I know this is going to sound strange, a little vertical line at x equals 2, because that's where we switch over. Now, I'm not going to create a table of values personally. I'm just going to graph these two lines. Now, it might be a little bit easier for me to think about this line as negative x plus 5, right? Because 1, 2, 3, 4, 5, right? And then I go with the slope of negative 1, down 1 to the right 1, down 1 to the right 1. Now, I stopped it right there because that's the cutoff point. And notice the equality isn't on that one. So I'm going to put an open circle there. And then I think I'm going to use this because it just makes my life a little bit easier, or a little bit neater at least. All right. Likewise, 1/2 x plus 2. Let's do that one. Now, granted, it doesn't apply right here, but I'm going to still put maybe a dot right there. 1/2 means I go to the right 2 and up 1, to the right 2 and up 1, to the right 2 and up 1. And that one's going to take off from there. Now notice, this actually turned out to be a continuous function because we filled in that hole. In other words, both of these have the same value when x is equal to 2. But look at D. Why does your graph contradict the answers you found in part B? Well, because it has no x intercepts. I mean, look at it. It's got no x-intercepts, and yet here they are, solved algebraically. So letter E then asks us, how can you resolve the contradiction from D? I mean, here's B. We found the x-intercepts algebraically, 5 and -4, and yet when we graph the function, it has no x-intercepts. Well, it's kind of cool. Taking a look at this function, right, we found that 5 minus x had an x-intercept at x equals 5. But that formula only applies when x is less than 2, and 5 is not less than 2. Likewise, 1/2 x plus 2 will be equal to 0. Well, that was at x equals -4. But that formula only applied when x was greater than or equal to 2. So -4 doesn't count. So actually, we're all set. And that makes piecewise functions very tricky because information that you get out of them, especially about x values, has to be checked compared to the domain intervals for which those formulas apply. That was kind of fancy. Anyway, pause the video now. Think about what we did. Write down anything you have to before we go on. Okay, here we go. Exercise 4. For the piecewise linear function f of x equals blah, find all solutions to the equation f of x equals 1 algebraically. So in other words, I want to know all the x values where the output, the y value, is 1. So see if you can do that. Okay, well, let's do it. I have to set both of these formulas equal to 1 and see what happens. -2x plus 10, let's set that equal to 1. That's going to get me -2x is equal to -9. And then when I divide by 2 on both sides, I'm going to get x equals 4.5. Now this formula only applies, though, when x is less than or equal to 0. 4.5 is not less than or equal to 0, so that one's not correct. Let's try 5x minus 1 equals 1. Well, if I add 1 to both sides, I get 5x is equal to 2. Divide both sides by 5, and I get x is equal to 2/5. Now this is correct as long as x is greater than 0. Well, 2/5 is greater than 0. So that's my winner. All right. Again, tricky, because it seems like we're going to get two very valid answers, and yet only one of them checks, only one of them works. Okay. Pause the video now if you need to, and then we're clearing this out, and I think finishing up. Okay, here we go. So today, we reviewed the idea of a piecewise function, specifically piecewise functions where each piece is a linear function. All right? These functions simply have different formulas for different parts of their domains. And that can be tricky, especially when you're using those formulas to find something algebraically. You always have to go back and check it versus the domain interval from which it came. Okay, I know that probably sounds kind of complicated, and we'll see piecewise functions throughout the course, so hopefully we'll get more practice on it. For now, let me thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.